So for this video I thought we'd try a wee experiment. For most of my hobby projects I tend to use this stuff, which most of you will be familiar with, Bureau board or strip board or whatever you want to call it. Recently I was using some of this copper tape to make some contacts for a keypad, and I found that it actually takes really well to solder, just as well as the copper on this. So I thought, if I ever ran out of it, would I be able to make my own using a suitable substrate? So let's test that, shall we? As for the circuit, we go with one of the very first things I've learned to build as a child, which is an astable multivibrator. For those of you with your minds in the gutter, it's not what you think. It's basically an oscillator circuit, alternates between two states. The way it works is each of these transistors takes a turn at being switched on, the timing for which is controlled by the RC network on each side here. So basically I've made this up, and on the back I've used the copper tape here. It's not the greatest, but it's for illustration purposes only. So let's build the thing. I've already picked out my components here. And before I forget, any points where the foils overlap and start some solder, because the adhesive layer can probably act as an insulator. There's the finished circuit. It's not the greatest, but it is a proof of concept. So let's fire the thing up. I'm going to power it from 5 volts from my trusty ATX bench supply. And it actually works. The quality of the solder joints actually was quite terrible, which I wasn't expecting. I don't know why that is. I don't know if it's got anything to do with the paper, but when I put this stuff over like the strip board, there was no problems at all. So I'm guessing it is something to do with the paper. But anyway, yeah, it definitely works. So going into a bit more detail about how this circuit actually works, it's not quite as straightforward as you might think. The first thing you need to remember is that a voltage, otherwise known as a potential difference, is a difference between 2 points, so it's not always referenced to zero. For example, when this transistor turns on, this capacitor will be charged to a certain voltage, and it will be that the positive end of this will be pulled to ground via the collector, and the negative side of it will be whatever it's charged to minus whatever the positive is. So you'll basically have a negative voltage on the base of this transistor, which will turn it off. And that's basically what keeps the circuit going, is that cycle repeats alternately for each side. We'll get to the maths in a second. First I'll show you what I mean about that voltage difference using my oscilloscope here. Can't actually afford a proper scope, so this is basically one of those module boards stuck in a case. It's not going to be super accurate or even readable, but it should illustrate the point I'm trying to make here. So if we just measure the one at the base of the transistor here, you can see it going negative until it hits the base emitter voltage drop. which is roughly 0.69 volts as I measured it. So just above the zero line there. And that's 2.56 volts per division. I doubt you can even make it out anyway. But yeah, just illustrating the point. Now, getting to the actual maths. This is a very popular circuit for people just getting into electronics, and there are a lot of sites that will give details about it in various versions of it. But I've yet to see a single one that gives an accurate description of how to calculate the timing. Some of them will give you the basic RC time constant, like 0.69 RC. Some of them will even give you the version for the 555 timer, which is just completely wrong for this circuit. It is based on the RC time constant, but there are a lot of other things to take into consideration, including the supply voltage. Basic formula for charging a capacitor is the voltage across it, VC, will be your supply voltage times 1 minus e to the negative t over RC, where RC is your R is your resistor and C is your capacitor. But we are not interested in that. What we want to know is the time it takes for the VC to reach a certain point. So what we do is first we get rid of that. So move over to this side. VC over VS equals 1 minus e to the negative t over RC. And you just take the inverse of that, which is negative t over RC equals the natural log of 1 minus VC over VS, which will give you t equals minus RC times ln 1 minus VC over VS. So the key to using this is working out what your VC and your VS are, and that's all to do with that negative voltage I mentioned earlier. For this specific example, this point here is going to be your positive rail minus the voltage drop of that LED. So that's about 5.25 volts minus about 2.7, which is 2.55, plus the base emitter voltage drop that it takes to turn it on. So that's 0.69 as I measured it earlier. So that gives you 3.24. That's your VC. And the VS is your positive rail plus this point here, which is 5.25 plus your 2.55, which is 7.8. So if your VC over your VS is that's 3.24 divided by 7.8 equals 0.415. Okay, so we want 1 minus that, and we want the natural log of that, times your negative RC, which is, I'm using 33k for the resistor, that's 33,000, times 47 microfarads, which is 0.000047, which equals 0.83. So your time for this is roughly 0.83 seconds. Let's test that, shall we? I'm not sure how this will show up. I mean, I haven't perfected my camera technique, so the frame rate isn't accurate. But from what I can see, that looks pretty bang on. The last point I'll mention is that as you change the voltage, it's kind of counterintuitive to what you would expect. So when you increase the voltage, it doesn't actually reduce the time. It actually makes it longer, according to the formula. And I'll leave that for you to experiment with yourself. And I think that about wraps up for this video. Thanks for watching.